All right, so today we are going to do notes 50. We're going to talk about growth and decay in real-world situations. All right, so we have a population growth of bacteria. So we got bacteria. In a laboratory experiment, researchers established a colony of 100 bacteria and monitored the growth, and the colony tripled the population every day. All right, so we're going to create an equation. Y equals, well, my initial value is 100. It's what I'm starting with. It's my y-intercept. So remember, we have y equals a parenthesis b to the power of x. All right, and it's tripling every day. All right, so there's my equation. All right, so now we're going to fill out this table. We're starting at 0 days, we had 100. After day 1, it triples. So after day 1, it gives us 300. All right, after day 2, it triples, and then it tripled again. So I can write that as 3 squared. So that's going to give us 900. All right, after day 3, it starts with 100. It's tripling every day for 3 days. That's going to give us 2,700. Okay, after 4, we're starting with 100. Oops, sorry. It's tripling every day after 4 days. After 4 days, be 8,100. And after 5 days, then we are going to get 24,300. Okay, and we can just put those in our calculator, or we can even go put this in Desmos and pull up a table. All right, now we're going to graph them. So at 0, we're at 100. Well, it goes from 0 to 1,000, so 100 is pretty close to 0 on this scale. Then it goes to 300, so it's a little less than half. And then it goes to 900, so we're almost at 1,000. Then it jumps up to almost 3,000, 2,700. Then it jumps up to a little over 8,000. And then it's going to jump all the way up to 24,300. So somewhere around there, way up there. All right, and we're just going to, we can see that this looks like it's taken off steep. All right, so there is our example. All right. Now we're going to talk about this a little bit later, but we can also do exponential regression. So remember linear regression? We had like y1 tilde mx1 plus b. Well, in this one, we're going to do a b to the power of x1. Okay, so where there's a y and an x in my formula, I would put a 1 behind them, and instead of an equal sign, we're going to do that tilde. So if I just had these points, I could do that and it would give me the equation. Or, I mean, it would give me the line. It would connect my line for me. Okay, but we don't need that right now. We'll come back to that. So remember, my starting value here was 100 because we started with 100 bacteria. And then it grew, it tripled every 3 days. So that's my B. So what does A mean? Remember, that's our starting amount. And above it, we're going to write y-intercept. And then what does B mean? It's my constant multiplier, and they may call it a growth factor. All right, so it says write in a function y equals a times b to the x in terms of t days. So what this is it wants to know the population after t days. This is another way to write y. So my a, we just said, was 100. Times, it triples every day, that's my growth factor. And then instead of x, it's wanting me to put a t in there for number of days, time. All right, so we're going to use this equation. And we're going to find out what about after 8 days. So I would put 100 times my growth factor of 3 to the power of 8. There's two ways to do this. I can just put this in my calculator, or I can put my original equation in the calculator, and I can pull up a table and see what the 8th day looks like. So either one will work. All right, whenever I put that in, I get 656,000. So on my table, it would look like this: 8,656,000. All right, let's talk a little bit about this. Sometimes we get scientific notation, which in 8th grade we learned was times 10 to the power of something. Well, in our calculators, in both calculators, it's going to say E. It's going to say like 1.97 E6. Okay, that's another way to write scientific notation, and it just means that I'm going to move that decimal 6 numbers. Okay, so if I had written it and I wanted to move it 6 decimal places, 1, 2, 3, 4, 5, 6, I fill the rest in with zeros, and that is 1,970,000. Okay, and this one wants to know how many days would it take for it to be at this amount. Okay, so in this one, we can go ahead and we can put our equation into Desmos, and we can start typing in days and see how long it will take to get to this amount. So in your Desmos, you can type in your equation, which was y equals 100 times 3 to the power of x, and then you can pull up a table. Okay, and you can start to enter in numbers for x. Okay, we know that 8 was 600,000, so we know it's going to be bigger than 8. So start plugging in numbers and trying them. See what you get to. All right, when you're done with that, I also want you to complete the back of this and get a check mark on it. Okay, so this, or get a stamp from me after you complete it. You're going to do the back on your own.